when we develop the model, is there any preference to use only the primary data, or we use all the data and feed it to machine learning or to optic analytics?
Primary data.
Yes.
Is it only the primary data, or?
I will repeat again, yeah. Is there any preference? We use only primary data, or all the data we feed into the optic analytics?
Okay. Actually, you basically it's a primary data. You feed the primary data to optics analytics, and then
peserta webinar Tiara hari ini, perkenalkan saya Regression Sitanggang, produk spesialis dari PT Tiara Vibrasindo Pratama. Webinar Tiara kembali hadir bersama Bapak Ibu, rekan bisnis kami, customer kami. Apa kabar semuanya? Kami berharap Bapak Ibu semuanya dalam keadaan sehat, sukses dimanapun berada. Oke, untuk webinar kali ini kita akan membahas atau berbincang mengenai topik yaitu meningkatkan kinerja aset dengan menggunakan machine learning analytic. Nah, dan bersama kami telah hadir salah satu prinsipal kami dari Emerson, yaitu Mr. Neurenji. Beliau merupakan Reliability Solution Business Development Manager dari divisi Digital Transformation dari Emerson. Hello. Hello, Mr. Neurenji. I think.
Can you hear me?
Yeah. Oh yeah. Okay. Okay. I can hear you. Yeah. Okay. Good.
Yeah.
Yeah. How are you?
Fine. I'm work from home also. Singapore also like 50-50. So 1 week work from home, 1 week work in office. The COVID-19 is making our life change.
Yeah. Many change in our life during
many change in the life.
Last 1 year. Okay, thank you so much, Renji, for coming on board to our webinar. And before we start with you, I will present a brief of Tiara landscape. It will take around 4 or 5 minutes. And here we go with Tiara landscape.
Okay.
Oke, Bapak Ibu, itu tadi Mr. Renji dari divisi Digital Transformation Emerson. Sebelum Mr. Renji mulai memaparkan topik hari ini, seperti biasa, kami PT Tiara akan memulai dengan Tiara Landscape. Nah, Tiara Landscape merupakan salah satu gambaran menggambarkan visi Tiara, terutama di diagram expectation flow, di mana kami tujuannya adalah meningkatkan kontribusi aset fisik dari customer kami terhadap kinerja korporasi secara keseluruhan. Nah, kita tahu bahwa mengelola aset selalu dimulai dengan mengelola risiko terhadap aset. Jadi di sini ada dua diagram. Pada Tiara Landscape ada dua diagram. Yang pertama yaitu expectation flow, kemudian ada information flow. Nah, expectation flow ini merupakan visi dari Tiara, yaitu tadi untuk mengoptimalkan kinerja, pencapaian kinerja terhadap biaya. Dan dari expectation flow ini kita lihat alirannya berupa kinerja terhadap biaya, dan nanti dari setiap aktivitas yang ada pada diagram ini, yaitu ada 4 bagian, yaitu ada PDM teknologi, kemudian ada condition management, ada reliability management, kemudian ada asset management. Masing-masing aktivitas ini akan mempunyai ekspektasi masing-masing, kemudian memberikan kontribusi bagi aktivitas yang lain. Nah, Tiara landscape ini menunjukkan interkorelasi atau hubungan dari setiap proses yang ada pada diagram Tiara landscape ini. Nah, kemudian dari information flow, dari katanya kita tahu bahwa nanti dari diagram ini masing-masing aktivitas akan memunculkan atau memberikan informasi yang kita butuhkan untuk mengambil keputusan. Nah, pada PDM teknologi akan menghasilkan informasi teknologi examination, kemudian pada condition management kita akan mendapatkan informasi asset wellness, kemudian dari condition management akan berkontribusi atau diterima oleh reliability management dengan memberikan informasi life cycle strategi. Kemudian ujungnya yaitu di asset management, di mana informasi yang diberikan yaitu keputusan berdasarkan risiko. Nah, setiap webinar yang kami lakukan setiap minggunya, itu akan selalu berkaitan dengan Tiara landscape ini. Nah, untuk topik hari ini sangat menarik, karena topik ini akan menyinggung semua aktivitas yang ada di Tiara landscape, baik pada PDM teknologi, condition management, reliability management, maupun asset management. Di mana kalau bicara machine learning atau artificial intelligence, kita berbicara data atau big data. Nah, salah satu data yang bisa kita ambil yaitu data dari PDM teknologi, yaitu berupa condition indicator. Nah, nanti di pembahasan kita hari ini, kita juga akan melihat machine learning analitik ini juga membutuhkan LCS review nanti ya di dalamnya. Karena di dalam machine learning analitik ini ada data Fmea, failure mode effect analysis, dan itu akan direview secara berkelanjutan untuk mendapatkan hasil dari machine learning yang improve dari hari ke hari dan dari bulan ke bulan maupun dari tahun ke tahun. Jadi kita akan melakukan juga LCS review di dalamnya. Nanti Mr. Renji akan menunjukkan white box. Jadi machine learning bukan hanya black box, nanti ada white box-nya di mana user atau kita dapat berkontribusi untuk mengimprove dari machine learning tersebut. Nanti akan ada demo dari Mr. Renji, dan nanti kalau ada pertanyaan atau diskusi bisa langsung dicantumkan di Q&A ataupun di chat. Nanti pertanyaan tersebut akan kita bahas di akhir sesi. Oke, demikian sekilas Tiara landscape. Kemudian selanjutnya kita akan dengarkan pemaparan dari Mr. New Renji.
Okay, thank you very
Mr.
much.
Renji, yeah, it's your time now. Yes.
You can hear me?
Yes, we can hear you.
Okay.
Yeah.
All right. So, good morning, good afternoon, everybody. So I'm Renji. I'm from Emerson, Singapore. So today, I think the topic of discussion will be how we actually apply machine learning in improving our asset performance. And if you are aware of the industry, right now, I think you may have heard that Emerson also acquires company that actually do machine learnings. And then this was a platform that has been used by many big refinery petrochemical plants in the world. All right, so I'm going to share this this platform. We call it, after we acquire this company, we actually rebrand it under Plumwhite Optics. We call it Plumwhite Optics Analytics. Okay, previously this is a product that is called Knowledge Net. Okay, KNet. Some of you may have heard, and it is actually widely used in Saudi Aramco, in ExxonMobil, in Shell. In using machine learning since 2010, they have started using this this platform to actually implement machine health monitoring, predictive and prescriptive monitoring using this platform. Okay, so without further ado, let's go into detail. All right, so as you know, in Emerson, we actually have different types of machine monitoring solution. Some are actually for online, critical online system. We have our equivalent of Bentley Nevada, our own prediction, as well as prediction plus protection system. Okay, and in fact, some are using our prediction system to connect to the buffer output of Bentley Nevada 3500 protection system, so that we add prediction on top of the BN protection system. So these are all can be wired to DCS, or they can be wired to our machinery manager software. Okay, and our we are also the market leader in wireless vibration. All right, so if you look at Shell in Singapore, all the plant are actually monitored using our wireless vibration. So in Asia alone, we almost sold 7,000 over units of wireless vibration. So we are actually one of the market leader in wireless vibration, as well as the portable. I think Tiara is actually so-called helping to this in using Emerson product to help customer to improve your rotary equipment prediction for their mechanical issues. All right. So now, so of course today this is not the focus. This has been there for almost 30 years, more than 30 years. Now today, the focus will be on the analytics. All right. So this, as you know, as I mentioned when I start the this presentation, it was a company that has been used by Saudi Aramco, Shell, ExxonMobil. It's a machine learning company, and then it has been applied in this site, and then help them to actually improve, further improve the health and performance of their critical equipment in the plant. Okay, so we are going to focus on this part. All right. Now, what is the objective, okay, of applying prescriptive analytics? Actually, later maybe you will figure out why we call it prescriptive. As you know, for a steam turbine or a compressor or a boiler, there is actually many potential problems that could possibly happen. Okay, clogged loop wire filter, high vibration, superheater regulation, station failure, and so on. All right, so there's many potential issues that can crop up during the operation. Now, all this can actually cause efficiency drop, as well as shutdown. Now, here is the most important part, whether we can actually find a system that can automatically provide early detection of this health and performance issue, and then automatically perform root cause analysis. And the third part is automatically provide corrective actions to the end user. So this is actually the objective. Okay, the objective is very simple. These three: automatically detect early symptoms of abnormality, and then automatically find out what is the root cause, and then automatically provide the corrective action. So this is actually the three most important objective of applying prescriptive analytics. So why we call it prescriptive? Now you can guess. It's like a doctor. The doctor doesn't just tell you there is a problem, but they also tell you what you should do in order to solve that problem. Okay, the health problem. So that's why it's called prescriptive. It's prescription. That means tell you what you need to do in order to correct that particular problem. Okay. So same for turbines. Same for compressor. you will have surging problem, you will have clockwork loop oil filter fouling inside the stage of the compressor, and then low discharge pressure and so on. So all these issues, again, will lead to high energy consumption. And the objective of applying all these prescriptive analytics is actually to detect this problem early and then provide the root cause to the end user and then provide the corrective action to the end user automatically by the system, okay, by the analytics. Okay, so this is again the objective. Now, so what we are trying to do is we want to move away from reactive and preventive maintenance. Okay, one is actually too late, the other one is too early. You are replacing part unnecessarily or doing a lot of checks or doing a lot of shutdown unnecessarily into using machine learning and artificial intelligence to help the prediction and the prescription of these abnormalities and the solution. Okay, so this is the objective, to move away from the top two and then move more towards the bottom. Okay, predictive and prescriptive. Okay, so just quickly dive into what you actually see when you use the system. Okay, so as I mentioned, Saudi Aramco has been using this system since 2010. Okay, many years, and then the result is very, very significant. They even speak for us on many occasions, and you can find the video on YouTube later. I can show you. So they actually speak for us, and they allow us to share their result publicly. So so basically, you is able to actually see all these intelligent dashboard that can actually point out what are the key KPI of concern, like maybe today there's a gearbox that needs your attention, and then what is the remaining useful life, major probability of failure, and then what are the different process units, okay, and their KPI, and also the if let's say some process unit has certain issue, then what is actually the equipment that actually causes those issues. Okay, so here you actually see that there is a compressor that has an anti-surge valve open issue, and then this is the prescriptive advice being given. Okay, and not just for compressor, actually all the equipment that you see, all the equipment, whether it's compressor, turbine, heat exchanger, and many other assets, they are all monitored by this system. And then anything wrong, the unit will be highlighted, and then the root cause will be identified automatically, and with the corrective action. Now, if you want to dive into the detail of what leads to this problem, you can just click on this hyperlink. Then you can go down to the detail. So in the detail dashboard, equipment dashboard, you can actually see 3 tabs. Okay, the first one is actually the overview. Okay, second one is a statistic, and the third one is the performance. I will actually show you one by one. Okay, so for the overview, you can actually see all the real-time readings of the compressor, including some of them are actually calculated KPI. Take, for example, polytrophic efficiency, or the head, or whatever, those that for the steams and all these things. So those will be shown in real time, what is the value. But if you see an exclamation mark, there is something wrong with this compressor. Okay, and what's wrong? The root cause is actually shown here. Okay, on your left hand side. So here you actually say there's a low compressor performance, and if you open it up, you can actually see the low compressor performance is actually due to low discharge pressure. Okay, and the low discharge pressure is actually due to anti-surge valve too open. Okay, so here it actually show you the drill down of the root cause, and this is not detected by human, but it's actually detected by this software. Okay, the software actually detect that there is this anti-surge valve too open issue. I will show you how we actually achieve this automatically. That means automatic root cause analysis. Okay, if you have a compressor performance drop detected by the system will automatically go and find out what is actually the root cause automatically. And then it will also, based on probability, it will also highlight some of the abnormality that could soon be happening. Okay, that could soon be happening. Not yet happen, but it could soon be happening based on past probability of occurrence. So it can actually predict certain things that is going to happen. All right, so you will highlight them in orange rather than in red. Red means it's already happened. This particular event, we call it abnormal event. All these are actually abnormal event. So that particular abnormal event has already happened, but this three has not yet happened, but the system predict that it could possibly happen. Okay, so if you click on the root cause, then at the bottom, this is the most important part. It actually shows you what is actually the corrective action. Okay, in the case of anti-surge valve, okay, so this is actually the anti-surge valve. So basically, if your suction is not enough, okay, suction pressure is not enough, typically the anti-surge valve will actually open, allowing some of the discharge gas to go back to the suction to actually maintain the suction pressure. But this is actually a waste of energy, okay, because your compressed air go back to the suction. But it's actually there to actually prevent the surging from happening. But if you are not actually operating near your surge line, why is your surge valve being so open, right? So the system actually detect whether you are actually operating near the surge line or not. And if you are not operating near the surge line, then your anti-surge valve shouldn't be that open. And then it will actually give you the corrective action, okay, to tell your team to check the surge valve and then see whether the valve is stuck or you need to actually close, do something about the valve. Okay, so this actually, the impact is there is a drop, excessive energy consumption and a drop in compressor performance, as you can see from here also. Now, here is a very interesting part. You will see that the blue color is actually the real-time efficiency versus the rate. So the rate is actually what we call a dynamic target. Okay, dynamic target is a target that is calculated based on your historical data. So it's a model that is created from your historical data using machine learning. Now, what happened is that the model actually, let's say you have 2 years of historical data of this compressor. You feed to the modeling software. There is a modeling software, later I will demo to you. So you feed to that modeling software. So what happened is that the modeling software will pick up those period of time when the compressor is actually performing at its best. Okay, and it will actually analyze the relationship between the input setting and the efficiency output of the compressor. And then from there, it can actually create a model to, so the input is actually what we call the operating condition. Okay, so you actually learn and then create a relationship between operating condition and efficiency. So when you, in real time, it will actually calculate, because different operating condition has different target, okay, has different so-called efficiency, best possible efficiency. That's why if you are using different types of inputs, it will actually lead to different efficiency. So the model is actually calculate a dynamic target rather than a static target. Okay, based on your different operating condition he learns from the past, it can actually calculate a dynamic target and compare that dynamic target against the real-time performance efficiency calculated using formula. Okay, so if the real-time and the dynamic target different by too much, then it will actually trigger a root cause analysis to find out why there is this gap in the performance. Okay, so this is actually the dashboard, for detailed dashboard for that. The root cause can have a lot. Later you will see the different types of root cause. Now at the end of the weeks or at the end of the months, there will be a statistic. This is a second tab. Okay, this statistic is telling you for this compressor, these are the most frequent occurrence of root causes that cause this compressor to underperform. Okay, whether it's compressor vibration or the surge valve, or is actually because of the loop oil system having some problem. Okay, and it also tells you some of the root causes that actually take a long time to resolve. Okay, persistent means it keep happening, and also it takes a long time for it to resolve. So what is the significance of this dashboard, of this statistic? The significance is that when you actually plan for your next maintenance, then when you look at this dashboard, this statistic, you know what are the priority to do when you need to perform the next scheduled shutdown or next scheduled maintenance, because it actually either tell you what are the root causes that most frequently happen and that happens for a long time and that cannot be resolved. So all these are actually being tracked in the system. Okay. Then the third part is, of course, things that we want to know from every day. What is actually the performance of this compressor? How does it? Where is the operating condition? Where is the operating point in comparison to the performance curve of the different performance curve of the compressor or the pump or the turbine? Okay, all these are actually shown on this dashboard. Okay, so it's actually indicating the all the different KPIs of this compressor. For you is for a compressor, you have almost up to 100 over KPIs defined by American Society of Mechanical Engineers, ASME. So they actually define 100 over these parameters, and then how to calculate this based on different input variables of the compressor. Okay, so this is actually the so-called ASME PTC standard KPI for compressor, turbine, boilers, and different equipments. Okay, you have this performance indicator. Okay, so just to give you more example, we just not just doing compressor. It's actually a lot of equipments in our library. So this is a boiler. So this is a mechanical draft boiler. So you can see that the boiler performance is low. Is actually due to water condition. Okay, water condition, and the water condition is actually due to, if you trace it down, it is actually due to the boiler feed water controller valve stuck at low position. Okay, so you actually identify this root cause and then tell you, if I were to make it bigger, so it will actually tell the operator to actually check the controller status and then do all the corrective action according to the corrective action prescribed. That's why we say it's actually a prescriptive maintenance. Okay, so it will actually tell what is the root cause. It will actually find out what is the root cause and then tell what is the corrective action to the operator or to the reliability engineer, so that they can actually take action. Okay, and then again, here is a model calculated efficiency compare against the actual efficiency calculated using formula. Okay, so that here there is a dynamic target. Okay, so again, you can see all the summary of this boiler, whether there's ID fan issue, whether there is a combustion air issue. You can actually see the summary of all this in the statistic dashboard. Okay, right. So in this machine learning platform, what we actually accumulated over the years, okay, of working with Saudi Aramco, ExxonMobil, Shell, and all these British Petroleum, all these key customers, we actually accumulated almost all the different equipment that you can actually find in a plant. Okay, so whatever equipment models that you are looking for, it's likely that we already have that equipment in our library. Okay, for doing this performance and health monitoring, for predicting the failure, remaining useful life, and failure prediction, and then having the automated root cause analysis models in our system, and also the interactive workflow. Okay, so these are so in all, we have 490 over Fmea template that is already inbuilt in this software. Okay. Now we want to go into, now you see what is the end user can see and also can benefit from this software. But Now we want to dive into the how. Okay, how is all these things achieved? Okay, so this is where so just now you can look at it and say, it's very interesting, but is it real that you can automatically find out what is the root cause and automatically find out what is the corrective action? How is it achieved in your system? Okay, so now I'm going into the how. Okay, so in order to understand this software, we call it Optic Analytics. Before we actually acquire this company, it is actually called Knowledge Net. Okay, KNet in short words. Okay, so why it is called Knowledge Net? Okay, there is a reason. Later you will see. Okay, basically it is converting all your knowledge into machine executable. So machine can take over humans to actually do the checking, do the reasoning, and then come out with the solution. So that's why it's called knowledge, converting the expert knowledge into machine executable. All right. So the quick things to understand is to see that this software actually has two parts. One part is the online. The online is the one that we put to the server and run in 24/7 to constantly monitor your boiler, your compressor, your steam turbine, your heat exchanger, to monitor them 24/7. Okay, that is the online. Okay, so the online actually consists of 4 very important parts. Okay, KMap is the one that you see just now. Okay, those are the HMI user interface. That the dashboard, the equipment details, equipment statistic, equipment performance, those are the KMap. Okay, it's actually the HMI. Now on the other part, okay, is actually here the green color is actually the root cause analysis engine and the root cause analysis model for each equipment type. So this is the part that actually is capable of automatically go and find what is actually the root cause. Okay. Now, in order to find what is actually the root cause, you of course need to have logics inside. Logics, right? Logics to detect what is actually happening. So you need all this logic. Now, so this all these logics is what we embedded inside as expert rules. Okay, it's actually the rules in the root cause. So all this is actually logics that actually used to perform root cause analysis. Now, so when the logics actually detect certain root cause, it can actually trigger a workflow to enforce certain SOP, standard operating procedure. So this is actually the workflow engine that actually execute the SOP. Take for example a shutdown of a compressor, a startup of the compressor, a startup of a boiler. Take for example. Okay, so I will explain this in detail later. Okay, now you may ask the question is like, okay, but where does the models come from? Where does this AI and machine learning come from? So this is the part where the modeling studio come into play. The modeling studio takes the historical data, and then you can actually do a lot of data analysis inside. And then once you do the data analysis, you can actually create models out of it. I will do a demo later for you to see. So you can create models that can be embedded inside your logics to predict certain things, like take for example remaining useful life, take for example the dynamic efficiency target of your compressor, okay, and compare against the real-time compressor performance, take for example, okay, and many other things. So you can actually create this model from your historical data, and then once this model is created, embed inside the rules, and the rules can be used to do the root cause analysis. Okay, now without further ado, let's go into the root cause analysis first. Then we go into the rules, then we go into the models. Okay, so this is actually the way how to understand this system. So the root cause analysis, let's take a look. Okay, so looks very complicated, but don't worry, this is not the end user interface. This is the engineering diagram of this software. Okay, so the software allows you to actually define what this is a steam turbine. Okay, and if you see there is a lot of this small little block here, okay, of what we call abnormal condition. Every of this block is actually an abnormal condition that can happen for this steam turbine. In fact, this is only half of the steam turbine root cause analysis. Okay, three. The actual one is actually much more complicated than this one. Okay, but we are not allowed to show because this is intellectual property. Okay, so but every of this node that you see is actually an abnormal condition. Now, so take for example, vacuum loss is an abnormal condition. Steam leakage is an abnormal condition. Okay, and maybe the low shaft, ceiling steam pressure low is another abnormal condition. Now, all these abnormal condition, all these things can happen to a steam turbine, but actually, all these abnormal condition has cause and effect relationship. The good thing about this software is that it allows you to define what are the abnormal conditions of this steam turbine, and also define the relationship between each of abnormal condition, so that it can be formed into a tree like this. Okay, this is what we call a Fmea fault tree. Okay, Fmea fault tree, or it's also called root cause analysis of these equipment faults. Okay, so it allows you to define. If you look at here, vacuum loss. Okay, vacuum loss. Take for example, I just make it bigger because it can be very small. So if you look at, let's say I detected vacuum loss, then the software will start to go and search whether this vacuum loss is actually due to condenser level low, or is actually due to separator tank out of range, or is actually due to the low pressure section shaft steam pressure low. Okay, he is going to find out what is actually the root cause. So so all these logics, actually each of these block inside has, each of these block inside has a detection logics, what we call rules. Okay, so each of this block has its own rules, this block has its own logics inside, and this block has its own logic inside. Okay, so whenever, and each of these block is executed per minute. Okay, it's executed per minute to actually constantly check for the steam turbine whether any of these abnormal condition. Okay, here I think we have at least 100 abnormal condition. So whether any of this abnormal condition actually happens. Okay, so if one of them actually detected to be true, then it will be highlighted in red color. It will be highlighted in red color, and this will start to trigger the checking of whether this is actually causing vacuum loss or this is actually causing the vacuum loss. And until you actually find the root cause, then that root cause will be highlighted in red. Okay, and then when this root cause is fine, it continues to search downwards to see what is exactly the cause of this. Okay, until you actually find the leaf, which is the root cause, then it will actually stop there to say that, okay, this is the ultimate root cause that caused my vacuum loss. Okay, so this is actually if you go in this direction, if you go in the forward direction, this is actually the root cause analysis. Now, if you go in the backward direction, this is called impact analysis. Okay, if you go forward, it is called root cause analysis. If you go backward, it's actually called the impact analysis. What does this mean? Is that impact analysis means that if there is a vacuum loss, if you don't resolve this problem, you will soon having a poor turbine performance, and then you will get a steam turbine performance drop issue. Okay, so you actually have root cause analysis and impact analysis by allowing you to define all the relationship between all the abnormality that could possibly happen for this steam turbine. Okay, so what happened is the system constantly execute all this abnormal checking per minute to check for abnormalities, and then automatically search for the root cause whenever a particular abnormality like vacuum loss is detected. Okay, so you actually perform the automatic search of the root cause. And what is the magic that allowed them to actually perform the root cause search? The reason is because every of this node, if you double click, it has a detection logic inside. There's nothing magical. You just have to have a logic inside. Okay, each of these node to detect whether this particular condition, abnormal condition, actually happened or not. Okay, yeah. So if you zoom out and think of it, what is this software trying to do? This software is trying to convert all your expert knowledge, the knowledge inside human brain. That means in our, let's say I am a turbine expert. I am actually a compressor expert. I have been working in this, I have been working with turbine for more than 20 or 30 years. And maybe I'm also retiring, okay? But what happened is that this knowledge can now be converted into a machine executable, okay? So this machine is taking the knowledge, program it inside, and then so that it can actually execute this human knowledge automatically whenever it detects any abnormality. And the good thing is, human don't need to be there detecting the abnormality. The system is actually detecting the abnormal condition automatically. And then when it detects, it automatically go and find what is the root cause, and it automatically go and find what is the corrective action. Okay, and this is also, you know, we have a lot of Fmea documents provided by the OEM, and this Fmea document is actually laying in our cupboards. All right, if nobody reads it, nobody actually learn all the troubleshooting or learn all the abnormalities that could possibly happen for this equipment. So all these Fmea documents are now being converted into a machine executable, so that they can, all this knowledge, whether it's a knowledge in human mind or the knowledge in paper document, now they can convert it into machine executable, and the machine is checking for this abnormality every second, every minute, and then automatically go and find what is the root cause if there's some abnormal condition detected. Okay, so this is the important essence of this system. Okay, converting all the knowledge into machine executable. All right, and here is the same thing. I just show you a simplified example of a compressor. Okay, of a compressor. So again, I'm actually converting all the Fmea document and also the compressor expert knowledge into a machine executable. Also, this can actually automatically find out why there is a drop in compressor performance, and then what is the root cause. It can be anti-surge valve too open, or it can be compressor vibration issue. Okay, now, so the question here is, what is this rules that is embedded inside each of these detection, abnormal condition nodes, right? This is a node, and then inside this node, there is a logics inside to detect this abnormal condition. So what is this logic? Let's double click and go into it. Take for example, I double click on the vibration, compressor vibration, double click. So you go inside, it actually have the logics to pull the vibration data from your system one, from your Emerson MHM, wireless vibration. You can actually pull all this data into this, and then he will check one by one, drive end, non-drive end, axial, whether it's the compressor or it's the turbine that drive the compressor. It will check for all this vibration automatically. And then there are certain threshold, there are certain limits inside that can actually do the checking. So this is a very simple logic for vibration checking, right? The vibration analysis is still done inside system one. The vibration analysis is still done inside the Emerson software. But this software basically picks up those information and then do the checking of the whether there is actually vibration. Is it because of high vibration that causes my performance to drop? Okay, and then take for example fouling, right? So compressor can foul in the in each of the compressor stages. The fouling can actually happen in the stages, and you can actually predict the fouling, okay, using standard principle formula-based calculation, or you can actually use machine learning calculation. That one I can show you later. So Just for example, a principal formula-based calculation is to take in suction pressure, discharge pressure, flow, and also temperature at different measurement point, and then calculate the index of compressor fouling, okay? And then put it inside the compressor fouling abnormal condition detection nodes here, okay? Put it inside here to actually detect, okay, compressor fouling. Okay, so just now, as I mentioned, there is this thing called anti-surge valve to open, which you also see in the dashboard just now, right? So I'm just need to switch over to the live system. So this is actually the software, as I mentioned. So this is my this is a demo. Actually, a compressor is actually much more actual implementation aside. The compressor logics is much more complicated than this. Okay, we actually make it simple because we don't want to show all our intellectual property to customer. Okay, so until there is an actual project, then you will actually see the full logics inside. So here is just half of the logics. Now, so you can actually see like if I were to run this, I can actually run these logics. Okay, and when this logic is run, so it will start reading. Okay, it will start reading from DCS all the different parameters related to this compressor, and then determine whether or not there is a loop oil clog, filter clogs issue, whether there is an anti-surge valve to open issue, or whether there is a fouling issue, or this. Okay, so let it run for a while. So I just minimize this. Okay, so right now it's actually downloading the logics and then start the engine running. This server will be running and then constantly reading the data, the real-time data from DCS, and then checking. Okay, just while we are waiting for it to finish so-called downloading all the logics to the runtime, let's take a look at the these logics. Okay, right now I'm a bit stuck because I'm running it through my laptop. So this is actually a server. Actually, I'm running using a virtual machine. Okay, so let me see. Okay, right now is okay. I can also search from here. Okay, all right. So by right, I can just double click and then I can go into the logics. So let's take a look at anti-surge valve to open the logics inside here. So this is actually very interesting. What it does is that you can see here there is a square called distance to surge. Okay, distance to surge, and the distance to surge is actually a model that is created, and this model is created from OEM data. Okay, they are model that is created from historical data. They are model that is actually created from OEM data. Now, if you open up your compressor OEM documentation, there will be surge line that is inside this OEM document. Okay, and what KNet can do is very interesting. You have a surge line chart in your either it's in a PDF document or something like that. The modeling studio, later I will show you the modeling studio. This is actually the modeling studio. It's actually below here. Later I will show you. So the modeling studio is able to convert your PDF document into a model here that can actually calculate where is your current operating point, the operating distance to the surge line. Okay, so this model will actually tell you how far away are you from surge, and if you are not close to the surge line, then it will actually check what is the opening of your anti-surge valve. Okay, the opening. If you are not operating near the surge line, but your anti-surge valve is wide open, it's actually wide open, then it will actually give you an alarm, okay, telling you that, hey, you are not operating near your surge line. Why you are actually your anti-surge valve is actually open, and also open widely. Okay, so that is actually the logics that is checking using a model created from OEM search line information and compare against the real-time valve opening status to actually detect whether you have an anti-surge valve to open event. Okay, so this is just one simple logic that actually detect whether you have anti-surge valve open to open event is here. Okay, so just now I said you can just directly come to here like this. Okay, so and then I can also look at some other things. So let's take a look here. There is this thing called compressor performance drop. Okay, compressor performance, low compressor performance. Maybe I just make it bigger. Okay, so maybe because some of you that maybe you are looking at a desk laptop and the screen may be too small. Okay, so you can see there's a compressor performance. So the compressor performance can be due to anti-surge valve to open. Okay, and it can also be due to clogged loop wire filter. Okay, and many other reasons. Okay, so but how do here in this compressor low performance, as I said, every of this node has a logics inside. Okay, it has its own logics inside. Every of this node has a logic inside to actually detect certain condition like clogged loop wire filter, taking in suction pressure, differential pressure, and all these things to actually detect logic. So what is the logic that detects low compressor performance? Let's take a look. Okay, so compressor performance, typically what we measure using polytrophic efficiency. Okay, polytrophic efficiency of the compressor, and there is a formula that governs the polytrophic efficiency defined by American Society of Mechanical Engineers, ASME. Okay, so this is how do you know what is the efficiency of the compressor is by taking in the compression ratio, discharge pressure, discharge temperature, and the suction temperature, and then put in the formula. This is actually to implement the formula to actually calculate. I think this one is still running, so there's no value yet. Okay, so so to actually calculate the real-time efficiency of this compressor. Okay, so this is actually a real-time efficiency. I think you wait for a while, then this one will have a value. Later you can come back and see. Now, but how do I know whether this is a good efficiency or bad efficiency? That is an interesting question, right? How do I know whether this efficiency is actually a good efficiency or bad efficiency? You see, it's actually compared against a model created, a machine learning model. Okay, later I will show you how this is created. So this model is taking in current operating condition like the speed, the suction, the discharge, the suction flow, and then the compression ratio. It takes in all these current operating condition, real-time value from DCS, and then it calculates a predicted target of efficiency. Okay, now, so this is a part where you will be curious to ask, how does it know based on this input, what is the target efficiency? Now, what it does is that it takes, this model is created from, let's say your compressor has been running for 2 years or 3 years, take for example, or many years, as many years as you can. You feed this data to the modeling studio, and the modeling studio will pick up those period of time when the compressor is actually performing at its best. And then it will automatically learn the relationship between the input parameters and the output, okay, of those best performing periods. And then now, once it learns, you create a model, you put this model online, and then you feed it with real-time input variables. Then it will be able to predict the target efficiency, okay, based on the past best performance of different inputs of different operating conditions. So this is why we call it a dynamic target, is because different operating condition, okay, different operating condition, it will have different target efficiency. The efficiency is actually not fixed, okay, it's actually based on different operating condition. Okay, so then once you have this target, it will be compared against the actual, okay. I think my laptop is very slow. Still, there's no actual calculator coming out. So, but right now it's actually running, but it's assuming there is a value here. Okay, so let's say this is 60, this is 71. Okay, so the real-time efficiency is 60, and then the target here calculated by the machine learning model is saying that you should actually achieve 71. Okay, then this is actually a big difference. So this is how it actually detect there is a drop in the compressor performance compared to the past. Okay, compared to the past when the compressor can be performing at its best during this operating condition. Okay, so this is actually how it is actually detecting, as we said, how does this block detects whether there is actually a low compressor performance. Okay, so now the question maybe is now, how does this block or this model get created? Okay, now this block, as I said, is actually created from historical data, learning using machine learning created from historical data, and this is where I want to show you. Okay, so I can actually create it from scratch, but it will actually take some time. So what I do here is almost half finished this project already. So okay, I create an efficiency modeling. Okay, this is what we call the modeling studio. Okay, as you see the name called Knowledge Net, just bear with it because we acquired this company and then we are rebranding it. We call it Optics Analytics, but the original name is actually called Knowledge Net. Okay, now this is the modeling studio of the Knowledge Net or Optics Analytics, or what you call right now. Okay, and okay, so first of all, you will when you create this modeling project, what you do is you will import, okay, data, huge amount of data from your historical database. Either it's OSIPy, PhD, any historian, it can actually connect to the historian and pull all the data out. Or if you want, you can also convert it into Excel file and then import into this project. Okay, so now what we want to do is we import all the data related to this compressor. And in this list of data, these are the different variables of the compressor, and then these are the different timestamp. And then you have energy consumption, and then you have all these different input variables. Okay, that leads to this energy consumption. So now, the first thing when you want to do modeling, you remember somebody say something to you, maybe, is if you have garbage data, you will create garbage model. Okay, so the first thing what we need to do when we come to modeling is to do data pre-processing. Okay, and in fact, when we do data modeling, data pre-processing will take up 60% of the time. Okay, you have 2 years of data, you need to clean it, because the truth is our sensor is not perfect. Our sensor has a lot of noise, sometimes it will have spike, sometimes it will have drift, sometimes it will have lost connection. All right, so that will result in something that you can see immediately is there is something called no data. Okay, so these are the NaN. Okay, so these are the missing data, and also there are some funny data that can come out from time to time. Like suddenly this value become very high compared to the rest, right? So the software has a lot of algorithms inside here to actually helps you to actually detect all these outliers. Okay, all these we call it dirty data. Okay, dirty sensor data. We need to clean them out. Either you clean it up or you actually smooth it out, smoothing, or you can actually apply sampling to actually do those kind of statistical algorithm to actually reason out the actual value. Okay, so just for example, you let's say I want to clean it up, I can actually just for example show me what are the missing values. So the software go and search for all this huge amount of data, which is there any missing data, missing sensor reading. If there is a missing sensor reading, what you would like to do? You want to do interpolation for those missing data. If you want to do interpolation, what is actually the algorithm you want to use for the interpolation to actually replace those data to a meaningful value, right? So the software comes with all this, or you can actually do an impute, okay, to actually replace this with certain values of this data. Okay, so for simplicity, of course, I can, in this demo, I just remove this data. Okay, if you have a lot of data, then you can just remove it. Just click finish. Then once you finish, then you will end up with, once you finish pre-process this data, you apply all the normalization, you apply all the matrix decompositions, and you apply all the data cleaning and interpolation, you will end up with a clean set of data. Okay, as I said, this is not easy. This one typically take a long time. About, let's say your modeling take 1 week to do modeling. Okay, you need to at least take 3 days to actually do the data cleaning. Okay, it is actually, the data cleaning is a time-consuming exercise. Okay, to make sure all your data is at least reasonable, not unreasonable. Okay, now once you have a clean data, then the next question is, hey, I wonder, what is the relationship of this variable to my energy consumption? Okay, so I can actually then try to actually understand the relation. There's this thing called correlation. Okay, so I want to understand the relationship between all these parameters, and then I can go into this correlation, and it actually can show me the correlation of this data. So I can double click. Now here it is actually analyzing the data and then show you that yeah, this is related to this. This variables is heavily affecting this variable. Okay, this variable is not so heavily affecting these variables. But the most interesting part is I'm more interested in what are the variables that is positively affecting my energy consumption or negatively affecting my energy consumption. Okay, there are some variables that I can actually don't need to worry about them in my modeling because they actually doesn't quite affect the energy consumption. Okay, so the modeling studio actually tells you, okay, these are the variables that actually affect my energy consumption. At least 1, 2, 3, 4, 5, 6. 6 variables are affecting my energy consumption. Okay, all right. So now I actually have some understanding of this. I want to know, is there any patterns of energy consumption? Okay, is there any any patterns that actually affect energy consumption? Now, when you talk about patterns, seeking of patterns, one very common approach in data science is using, you go to modeling, and then this is a lot of this are actually, you have millions of data, but is there some data that are actually having the same behavior? Okay, same correlation, same behavior. Okay, so those data that has the same behavior will be grouped into, through this principal component analysis. You can actually Google PCA or principal component analysis. Basically what principal component analysis is that it actually group data of similar behavior in different dimensions, so that you can actually see a patterns of those data that is related to one another in one cluster. Okay, so I want to actually identify what are the possible patterns of energy consumption for this equipment. So I can actually use a PCA, and then I can actually select all these variables, and then I allow it to analyze to see whether there are some of these data are actually related to one another. Okay, so it actually show me there are a group of data set that are actually related to one another. A group of data set are related to one another, and then here there's another group that is related to one another. I make it bigger. Okay, so this is what we call different operating condition. These are the result of different operating condition. Later I will show you what does it mean, because now you actually start to see that the analytics actually telling you that this, I found there is some relation between this set of data and some relationship between this set of data. But we don't know what is the thing that actually separate them yet. But we actually can use PCA to find out there is some relationship between certain set of data. Okay. Now, what are these that is in the middle? What are these that is in the middle? Okay, sorry, yes, so my PC is a bit slow. So that is in the middle is actually what we call the transition. Okay, when it is actually transitioning from this operating condition to another operating condition, there is this transition data. This transition data is not meaningful to us because when we do modeling, we want so-called steady state. We don't want a transient state when we do modeling, right? So the transient state have to be thrown away. We want to analyze the energy consumption based on the steady state when it is actually running in a particular condition, rather than when it is transiting from this condition to another condition. Okay, so what we will do is we will delete all this transition. Okay, so I will just delete all this transition. Okay, delete, and here, delete. Okay, so I will delete all this transition. Okay, so once I delete it, then the next thing I can do is to actually label it in, create a new cluster. Yeah, I label it, I call it operating mode 1. I don't know what is this yet, no worry, later you will find out, okay, no issue. Okay, so I just give it a name first. Okay, easy for me to actually call it. So operating mode 2. All right. Then, okay. Then here I will say create a new cluster. I say operating mode 3. All right. So these are 3 different operating conditions that I call it operating mode 1, operating mode 2, operating mode 3 of this compressor. I don't know what it means yet, okay? But what I can do is that I can ask the software to help me to actually split, okay, to extract these 3 set of data, okay? Yes, okay, to extract this, to actually create a new table that actually label, this set of data are actually operating mode 2. And then there is some set of data, if I scroll all the way down, some set of data are actually operating mode 1, okay? And some set of data that is operating mode 2, okay? So this allows me to split out the data into operating mode 2 and operating mode 1 data and operating mode 3 data. Okay, now I have 3, instead of 1 table, I have 3 tables right now. Okay, each table is different operating mode. Now, if I look at something very interesting, if I look at operating mode 3, do you take note that this is operating mode 3, right? Yeah, operating mode 3. You take note of the energy consumption. It's about 500 to 600, around there, right? 500, mostly 500 to 600. You take the look at operating mode 2 of the compressor, it is about 400 to 300, the values, right? If you look at operating mode 1, it is almost 0. So when you look at this data, right, you start to have something, it's very interesting. It picks out the patterns. And then once you look at the patterns, you can actually tell this is when the compressor is not running, almost not running, right? Almost not running. So it is a different operating condition of this compressor, okay? And if you want to model energy consumption in operating mode 3, if you have 1 table that has everything inside, your model will not be accurate, because as you can see here, if now I split into different operating mode, you realize that different operating mode has different has different energy consumption, right? This one has higher energy consumption compared to this one, lower energy consumption. Okay, so if I want to model, I need to split. I need to use this just now, if you remember, I need to actually use PCA to split, to actually recognize different operating mode, and then after that split them up into different data set. Okay, and then once I arrive at this data set, then I can actually accurately create a model. Okay, now what does a model do? Now you have a data that says if I have these variables at these settings, I will have this energy consumption. Okay, if I have these settings, I will be in this energy consumption. So what it's actually doing is that what it's actually doing is that it will, you want to find out what is actually the relationship. And then, so that is the point of modeling. Okay, I want to find out the relationship between all these input variables and the energy consumption. So the simplest way, so here is all the machine learning algorithms you can actually use. You can use neural network, you can use regression, you can use vector machine, naive Bayes cannot. This is a classification methods. Okay, you can typically select, because these are analog data. Okay, so you can select any of these regression approach, right? So let's say I choose linear regression to find out the relationship between, to learn the relationship between the input set points and the energy consumption. All right, I use the linear regression, and then I say I want to model my energy against all these input variables. But wait a minute, I have so many input variables, right? But remember one thing just now, remember this correlation map here? Not every variables actually affect energy consumption. There is only a few that actually affect energy consumption. So when you want to do modeling, you need not actually include all the variable to do the modeling, okay? So I just select linear machine learning again. I choose the energy, okay? But I want to model here, sort the input according to correlation, okay? I only want to select the top six, because just now you saw 6 bubble, right? So those are the biggest contributor to my energy consumption. Okay, so I can select those top 6 that is affecting my energy consumption the most, and then use it for modeling. Then once I click, I'm okay, I can just, okay, 4K4 is okay. Then I can just click okay, and then it will start learning. Okay, it will start learning from the data, and once it learns, yes, it comes up with a models. All right, so this model is actually helping you to predict the energy consumption based on these variables. Okay, it learns from the historical. I have just now maybe few 10,000 records of data, historical data. Now it actually comes up with a formula that using those 6 variables to actually predict the energy consumption. Okay, predict the energy consumption. Now, why is it a formula? It's because I'm using a linear regression. Linear regression is using formula. Later, if I use other methods, you won't see a formula, okay? Because linear regression, polynomial regression is actually using formula, x cubed, y cubed, and all these things, all right? So how do I know whether this model is accurate or not? Whether this formula is of predicting energy consumption is actually accurate or not? Is how do I see? Of course, I can use my eyes to see. This is the formula calculated energy consumption. The blue color is the actual energy consumption of the historical data, right? So I'm comparing how close I am with that historical data, right? So it looks quite accurate, but is there any indicator that tells me how accurate it is? What percentage? This R square. R square is an indicator of model accuracy. Okay, R square equals to 1 is 100% accurate. R square equals to 0 is garbage. Okay, this model is like as good as garbage. So if you are something greater than 0.7, which is 70% accuracy, then that model is considered good enough, okay, to be put online to predict energy consumption. But I get a model that is 89%, so it is actually quite good. So this model is actually quite good. But I am curious whether I can actually create a better model. Okay, a better model out of this this set of data. So I come back to this data again. Okay, this time around I don't want to use linear regression. I use neural network. Okay, I use neural network. Now, the thing about neural network is that it will actually, just like human brain, he looks at, but of course it's actually smarter than human brain in the sense that it can process large amount of data, not like a human. So I actually say, okay, I don't need to select which are the variables that is actually affecting the energy consumption most. You don't need, because neural network, the more iteration you go through, the more it will figure out itself which variable actually affect energy consumption the most. Okay, so neural network basically is just like human brain. It actually learns through looking at the data and then create a relationship mapping in the form of a very comprehensive network of neurons. Okay, and then the neurons are linked up to one another so that eventually you can predict the value. So I select, these are my input variables. I don't need to care whether they are affecting the energy consumption or not. The neural network will figure out. Then I choose the layers of this neural network I want to use. Then go through 5,000 of iteration. Then I can start the learning. Okay, you can see that the neural network is actually running right now. It is actually learning from the historical data. You see here the iteration keep increasing until 5,000, it will actually stop. Okay, so what the neural network is trying to do is that it is actually creating a comprehensive network of neurons inside, and then this comprehensive network of neurons allow it to actually derive the conclusion of, if you have these input variables, what will be the output. Okay, so it is actually creating something that is like human neurons. Okay, so all this, of course, every one of this node is actually mathematical formulas inside. Okay, and then these neurons will, if he derive is this, then he will lead to this, and then reduce to this, and then he will further reduce until he come out with the result. Okay, so it's actually running through. You see, it's running very slow because my laptop is very slow. So it's actually learning through the historical data and then creating the relationship between neurons, and then coming out with the model. So of course, I'm not going to ask you to wait until it runs at 5,000. So I'm going to stop it. Once I stop it, okay, and then I say, okay, by right, I should wait until 5,000. But now I don't have time to wait. So, but it has learned, and he has created a model for me. Okay, even though I stopped at about 600 iteration. So it created a model for me. It looks very accurate, but remember what I say. The red color is actually the neural network calculated energy consumption, and then the blue color is the historical energy consumption. Okay. Now, how do I know whether this neural network model is actually accurate or not? Look at here, right? I say the R square, right? The R square, if it's closer to 1, it is actually very accurate. If it is closer to 0, it's a garbage model. Okay, so this is 0.96. Remember just now when I use regression machine learning, right? If I use regression machine learning right now, just now, what R square I achieve? Just now the R square is actually 0.89. Okay, so which one is better? 0.96 or 0.89? Okay, of course, 0.96 is better. So this is actually a better model that I can use to actually predict the energy consumption. Okay, so that's why I want to use this model. So if I decided to use this model, I can right click on this model, and then I say build as library. Okay, I will build it as a library. So once I build it as a library, I can drag and drop this library in my logics on the detecting on my logics of detecting low compressor performance. Okay, remember, right click here, I go into polytrophic efficiency. Where does this block come from? This block come from the model that I created from here, from my modeling studio. I export out this, I create a library, and then I can put this library inside my logics. So this will become my prediction of my energy consumption based on the machine learning. And then it will compare against my actual real-time efficiency. And then if my actual real-time efficiency, I don't know what happened today, it used to have a value. I think I need to restart this thing. So so here is my actual efficiency, and is compared against a model calculated efficiency. Okay, if this value is different than this value by too much, then there is a performance drop event happen. And when the performance drop event happen, then it will actually trigger a root cause analysis to find out what is actually the root cause that actually causes the performance of the compressor to drop. Okay, so that's why, so that coming back to the slide, okay, so now you understand how it actually works. Okay, basically there is a detection of compressor performance drop against the historical performance, against the past performance model using machine learning. And then once it detects there is a drop of compressor performance, it will automatically activate all these logics to check whether there is a low discharge pressure, or whether there's a high vibration, or whether there's an anti-surge valve to open. All this has its own logics. All this logic inside can embed models inside to actually do all the prediction inside each of these nodes. Okay, different models are created for different purpose. Okay, just now I created a performance models. I can also create an anti-surge valve models. Just now, as you see here in my this machine, anti-surge valve, right? I have a model inside also. This is my surge distance to surge model. Where is this model coming from? This model comes from the OEM surge diagram. Okay, so the software has a way of converting the PDF readings into a models. Okay, so just example. I think I did it once, but that one I need to open up. So I use a video to actually show you. Yeah, here you can see how this model is created. Basically is by taking the OEM documents and then convert the document into a models. Okay, very strange, right? How can the models being converted? Yeah. How can a model from a document being converted into a model? So here is your search line diagram. Okay, you can actually convert them. Okay, it will actually be converted into this, and then you create a model and then put this model here. Okay, so from your OEM document, it can be convert into a model as well. Okay, so so each of these block inside, okay, you can have different models to actually detect. Some of them don't have models. Take for example, just now I was showing like this what is that? The fouling, compressor fouling. You can choose to use model, or you can just use calculation principle formula. First principle thermodynamic formula to actually calculate the severity of compressor fouling. So depend. You sometimes need to use model, not always, because sometimes principle formula-based detection is very accurate. Okay, sometimes model is actually very useful. So you can mix and match. Okay, so it doesn't mean that you have to use. Just tell you the past experience. A lot of AI project fail because the vendor say that oh, you need to use AI in order to detect or predict things. Wrong. This is a totally wrong concept. AI cannot predict everything. Okay, a lot of prediction can be achieved by using simple formula to actually figure out there is a trend moving up, the rate of change is too much, and all these things. So you must actually combine. That's what this software is so interesting. You must actually combine principle, formula, rules, statistic, and plus the machine learning in order to any methods that can help you to detect abnormality, that can help you to predict abnormality. You must be able to apply it inside this detection, automatic detection software. So if a software only allow you to define machine learning or artificial intelligence, you must throw away that software because you will actually fail. Okay, not the model is actually, a lot of model is actually not good enough to predict things. So you must actually work in combination of principle formula, work in combination of statistical models and also rules. Okay, this so-called rule-based like just now you see the root cause analysis tree, that is actually a rules. Okay, so you must, your platform must cover all the different analytic methods, not just, oh, because machine learning is the most advanced. No, it's not true. It's simply not true. Principal formula will always be there to detect efficiency drop, to detect fouling, take for example. It's still very accurate and it will still be relevant. The only thing is machine learning can learn from the historical data. It can actually learn what is the best performance and then compare against the current performance to see whether there's a drop. And it can use to predict the remaining useful life. So there are certain things machine learning is very good to use. There are certain things principal formula is very good to use. There are certain things statistical models is actually very good. So we have to have a software that can allow you to use all of this. Okay, not just one of them. Okay, so this is a platform that actually incorporate everything. Okay, and not just incorporate everything, it actually incorporate everything in a white box manner. Do you realize that you can actually see all this logic very clearly? You can actually see how we actually take, for example, I just show you, I keep showing compressor, but let me show you something else. Let's say pump, right? Yeah, so this is a pump. Okay, a pump, of course, this is a pump. You can have a speed controller issue. You can have a clogged loop oil filter issue, bearing issue, and all these things, right? So you do you notice that all these logics are actually white box? You can change them. You can actually if I stop it, let's say I stop this one. Okay, I exit it. Now I can actually change all these logics. Okay, what I mean is that you, as a engineer, if you, okay, take for example, maybe I show you another one. These are not, or just, these are the equipment we are allowed to share. Actually, we are 100 over equipment in our library, but we are not allowed to show it. Okay, so heat exchanger, take for example. So these are the different abnormal condition of heat exchanger. Now, if I found more heat exchanger, what I can do? I can drag, I can create more correlation between different conditions. Okay, and then I can also define the logics. I can actually go inside, and then I can actually change the logics inside the detection logics. I can modify it myself. I can actually add in this statistical, temporal reasoning, data controls, all this inside here to make these logics more intelligent. Okay, and then I can also apply machine learning. Okay, I can also apply machine learning, create a library. Just now, as you remember, create a library, and then embed this library inside my logics to actually compare or to actually predict. Take for example, show you remaining useful life. Okay, remaining useful life of my compressor. How is it predicted? It is predicted using operating time, polytrophic efficiency, using polynomial regression. Okay, so what I know is actually here is actually polynomial regression. Okay, so it's actually using polynomial regression machine learning models to actually calculate the remaining useful life. The remaining useful life of heat exchanger is calculated using fouling index and operating time. All right, so it is the model that is created from the. Of course, a remaining useful life is more complicated when you do the modeling, because you need to figure out the period of time when the compressor is good and the period of time before it actually breaks down. And then using that set of data, the machine learning will actually learn from good to bad what is the patterns. And then he will learn from that pattern using different regression algorithms. And then after that, it can be deployed here to actually predict it. So, so there are places where you need to use models. There are places where you simply just can use calculations. Okay, calculations. And then there are places where you can use all the different statistics, SPC algorithms to actually, or the different methods to actually reason out whether there is this abnormal condition happen or not. Okay, so a good so-called industrial software for this detecting equipment abnormal condition is actually one that actually combine principal calculation and machine learning. Okay, not just only doing machine learning. We have seen in the market so many vendors actually promise the magics of machine learning and then offer only machine learning but fail very badly. So we want you to take note that you must find a software that can allow you to use all these methods, principle and also data-driven methods, statistical and also rule-based and also machine learning. This is very important. Okay, yeah. So just to show you what actually happened at the back is this root cause analysis constantly checking per second, per minutes, the condition of the equipment, steam turbine, boilers, compressor, and so on, constantly checking. And then if it detects something happen, then it will start tracing what is the impact. Okay, or if it detects something that happened in the middle, like here, it will actually trace down what is actually the root cause. Okay, so this is an engine that can actually do all the early detection of abnormality, and automatically trace down what is the root cause and automatically provide the corrective action. Okay, based on this unique execution engine, and it allows you to define the correlation between this abnormality and this abnormality. Actually, each of the abnormal conditions are actually related to one another. Right? So they are actually not standalone. One abnormality can lead to the other, and one abnormality can be caused by another. Okay, so this is very important. A software must allow you to define what is the relationship between abnormal condition. Okay, so once the system actually detect abnormal condition, then it can actually trigger workflow. Okay, take for example a drop in compressor performance. As a simple workflow, you may just want to actually inform the responsible engineer to maybe look into this issue. Okay, and if this condition continue to be rate for more than 2 hours or 3 hours, then you may want to escalate to the manager, right? So this is actually a so-called a workflow, a simple workflow that can actually helps to make sure the escalation is properly done, right? Now, but it can be a complex one that we done for Saudi Aramco. So it can be a complex of interaction between operator and DCS. So some of these steps of the workflow that get triggers when an abnormal condition happen, it can actually interact with DCS, right to DCS, maybe perform a startup or a shutdown. Okay, of course, with prompting the operator to check certain things before the system actually set particular value. Okay, so it can actually write to DCS, it can actually read from DCS, it can actually prompt the operator with the required alerts, and also the on the DCS panel showing up the instruction to do certain things using a workflow. Okay, so this will actually enforce a standard operating procedure to be followed whenever some abnormal condition is detected. Okay, so in short, what happened in summary is all your plant data, historical data, real-time data is being analyzed by the rules. Okay, it's analyzed by the logics, and the logics will trigger root cause analysis, right? And the root cause analysis will trigger workflow. Okay, so now you see the full picture, how this system actually works. So you have the rules, you have the rules will actually read the data from all your historical data, real-time DCS data. You have system one, you will read from the system one, and then after that, it will actually trigger root cause analysis. Okay, and then the root cause analysis will trigger a workflow. All right, yeah. So this is just a very small set of customer that we actually that is currently using KNet. So you can see, I think our largest install base is actually Saudi Aramco. So the largest refinery in the plant, not one of the largest, is actually the largest refinery in the plant, is Saudi Aramco Optic. So this is actually the plant that produce more than 10% of the world oil, right? So this plant is actually using KNet. In fact, now they actually move on to be used to turn it into energy optimization. Later, I will share with you energy optimization. So all these Saudi Aramco, this ExxonMobil, BP, Shell, all these are actually using this KNet, this knowledge net, this software, before we acquire them. All right. So and we continue to support this customer and expand. Right now, Saudi Aramco expanded to 6 plants already. Okay, in Saudi, all using this KNet. Okay, so this is not our slide. This is actually Saudi Aramco slides. So what they successfully do is they monitor all their critical equipment, compressor, turbines, and so on, and then achieve at least 22 million. Actually, this is 2015 data. I don't know what is the latest, but at least in 2015, there is 22 million of saving per year in terms of energy reduction, because they can actually figure out which equipment is actually consuming the most energy, and then why consuming the most energy, and what is the corrective action you can take. Okay, so they speak for us on the ARC forum. You can just go to the YouTube here, by this link, and then you can just listen to what they actually share about this KNet implemented in their plant. The most important part here, beside energy saving, and also this is most important, shorten the problem detection to problem resolution cycle time. So in the past, you detect the problem too late and also take a long time to resolve the problem. But now with this machine taking over human to actually detect all these problems automatically find out what is the root cause, automatically provide the corrective action, the problem to resolution cycle time significantly reduced. Okay, so that is, you can just go to the YouTube and then watch the video. All right, so what they take it one step further is actually to transform it into an intelligent energy KPI system. So when these energy costs start to go up, all right, you can see some of the different process unit has different production unit has red traffic light coming up, and then telling you that there is an inefficiency of a particular, in this case, it's a compression train. And this compression train is inefficient because there is a fouling detected by KNet. Okay, and then what is the corrective action and advice? And all this can be detected automatically, as you see here: exchanger fouling, valve stuck, or plate filter, or a fan issue, ID fan, FD fan issue. So all this can be detected automatically and then highlight on the dashboard, and you can click and drill down to the details. All right. So what they do is they start with monitoring all these boilers, compressor, gas turbines, heat recovery, all this equipment. They start monitoring their health and performance. After that, they roll it up to the product level, to the individual product level, so that they actually can trace why a particular product is taking more energy to produce than necessary, which are the contributor, okay, of this energy consumption. Of course, energy optimization has another part. Another part is actually using solver. Using solver to actually find out what is your objective, what is your constraint, and what is your variables. And then from there, I actually modify the variables to actually maximize my objective while live within the constraint. Okay, so that is the optimization using solver. But energy efficiency has another part. Okay, that is to find out which are the energy guzzler or high energy consuming equipment. Okay, so that is two places of how you actually can save energy consumption. Okay, yeah. So so we are not going to go into optimization because that is not the topic of today. So today is more on the equipment health and performance monitoring. But we just want to say that even when you monitor the equipment performance and health, the side effect is that the positive side effect is that you will improve the plant energy consumption also. Okay, so I'm not going to talk about solver. Okay, so this is using non-linear programming or mixed integer linear programming to actually solve what is the lowest energy cost that can produce all the demand that I need. Okay, what is the lowest? So this one is somebody interested, we can actually have another session to talk about this. Okay, so there is three areas we call, this slide still haven't changed the name. Now it's called optics analytics. Previously it's called KNet. So three areas of application. equipment performance and health monitoring. As you know, early detection of abnormality, automated root cause analysis, corrective action. All right, automated corrective action. The other one, as you see just now, the Saudi Aramco use case, it converts into a smart energy consumption and optimization solution. Actually, there is the third area. If you look at the plant as let's take for example distillation column as one big equipment, you will also have root cause. You will also have abnormality, right, for your process unit. Maybe it's a hydrocracking unit, maybe it's a distillation unit. So your process unit can be seen as one large equipment. And then inside this large equipment, there are various abnormal conditions, right? And there are relationship between all these abnormal conditions, right? So you can also use KNet to actually monitor and find out why there is a, take for example, column flooding, why there is a column flooding, what is the root cause, and all these things. So it will actually tells you what is the root cause, and without you having to figure out yourself why there is a column flooding suddenly happen. Is it because why is that? Is it because my this feed is blocked, or maybe it's because of my reflux having some issue? So all this is actually can be detected automatically and search for the root cause automatically by KNet. So this is just a quick, because this is not the focus of today, but just want to let you know that KNet can also be used and is also widely used in process industry to actually detect abnormal process condition. Okay. Yeah, so so I'm not going to go into too much of this because these are more on the process abnormal condition monitoring. Okay, so I think I finished my presentation. Just I think not sure whether there's still time, but I'm open for Q&A.
Thank you, Renji. Great presentation. We have many questions here, and we will discuss some questions. I already have some good and interesting question, like from Pak Prabha. The question is, can the machine learning model include ambient reading like temperature, pressure, wind direction, or others on defining performance baseline? Yeah, of course, temperature and pressure can, right? But how about the wind direction?
Wind direction, yes, it can, but you need to first have the measurement. If you have the measurement, just now as I show you, when you come to do machine learning, right, you can pass any variables to the machine learning we call it modeling software, modeling studio. So just, you notice that I actually just pull all the data from my historian related to compressor. Of course, you don't pull any data that is not related to this equipment. You pull data related to this equipment, and then it will, just for example, it will actually figure out what are the variables that will actually affect particular, take for example, energy efficiency or something like that. Yeah, so then it will actually generate this kind of it will actually find out the correlation automatically for you. Yeah, so the more measurement you have, the better. The software is capable of finding what are the variables affecting a particular output you are looking for, and also it can also find the patterns. Okay, like this set of data, there is several data sets seems to be related to one another. This is using principal component analysis. So it doesn't matter if you have wind data, you have flow data, you have temperature data. So long as the measurement data is available, feed it to the modeling studio, it will actually figure out the patterns as well as the correlation for you.
Okay, I think it is very clear. Yep. Thank you. And the next question is, I think already answered by you, but I will read the question again from Pak Gusti Pramana. When we develop the model, is there any preference to use only the primary data, or we use all the data and feed it to machine learning or to optic analytics?
Primary data.
Yes.
Is it only the primary data, or?
I will repeat again, yeah. Is there any preference? We use only primary data, or all the data we feed into the optic analytics?
Okay. Actually, you basically it's a primary data. You feed the primary data to optics analytics, and then some of the data, like when he tried to find the period of time when the performance of the compressor is the best, it will actually use its own formula to calculate. You can actually specify a formula to calculate the efficiency based on each timestamp, right? And then he will calculate a KPI for those records. Like, take for example, so these are the primary data. I assume what you say primary data is a raw data from the measurement, but based on this, it can actually calculate a particular KPI, whatever KPI you can calculate. You can specify a formula, then one more column will come out. Those are calculated. Then you it will then also use that calculated to do the modeling, because it's important, because the calculated data is making the modeling more easy to correlate. So you will have to use primary data to come out with the KPI, and then use the primary data plus the KPI to come up with the model.
Okay, and this is many customer asking about how about the connection or communication between optic analytics or Kinet with the other system?
It can connect to any system.
Any system, right?
Actually, there is one thing I didn't, because time is short. We have something called Optics has something called a data lake. So data lake, basically the purpose of data lake is actually to pull in data from any system. It can connect to system one, pull the data from system one. It can connect to Yogawa PRM. Take for example, if somebody is using PRM, I know, it pull in the PRM data. It can also pull in the data from Honeywell PhD into this data lake, and then KNet or Optics Analytics will actually read the data from the data lake and then process it. So you can connect to any system. In fact, we are doing
good. I think it is very clear. And I have last two questions for you, Reggie. It's from me about regarding to machine learning and artificial intelligence. By the way, how do you see the machine learning or optic analytics or artificial intelligence in the next 2 years or 5 years or 10 years in industrial plant?
It will certainly, actually it's not evolve, it already is right now. Certainly a lot of forward-looking plants are actually using it to optimize the profit. The thing is, it can first thing, what is the benefit of using machine learning? Of course, we or analytics in general is actually to help you to detect the problem early, and most importantly, automatically. Last time the problem happened, then somebody realized it, then it's already too late. So it is a thing that is detecting the abnormality every second or every minute. Every minute is detecting all the different abnormalities, whether the abnormality happened or not. And then how it detects is, of course, using all the different analytics models and also the principal formula statistic. So this actually shortened the problem detection, and then also to the resolution cycle time. And then this helped to optimize your inventory and also make sure your equipment is up 99%. More like 90, if let's say it's 90%, now it can go up to 99%, and this will help with the productivity. So it is already happening. And in fact, yeah, in a lot of big plant is already investing heavily on this. Yeah.
But for next maybe 5 or 10 years, I think it is a must, right?
It's a must. I think. Yeah. If you look at Petronas, if you look at PTT Thailand, they invest millions on AI right now.
Yes, I agree. Millions. It is a must for next 5 or 10 years.
Yeah, because if you still wait for human to reason it out, it's actually too late, or even detect it. You detect it's already late. The system is detecting automatically at the back and predicting. So if you still rely on human to detect it, first you detect very late, and then you have a long period of time to figure out what's actually the root cause. Yeah, so that is very inefficient.
Oh yeah, Randy, we have another question. We still have time, I think 5 minutes.
Yeah. Okay.
From Pak Rafika. For starting equipment like... I saw that. Yeah, you read the answer, right? For starting equipment like red vessel. Sorry?
Yes. Yeah. So I'm showing the am I sharing my screen? Are you seeing my screen right now?
Not yet.
No, is it? Not yet.
Okay.
One moment. I think I am screen this one. Okay. So hope that you are seeing my screen. Yeah, okay. I think I saw that. So I'm actually showing the give me a second. Heat exchanger. Okay, so in the heat exchanger, I actually has the equipment, but just one moment. I just want to show a bigger picture. So heat exchanger, you have a different abnormal condition, fouling, leakage, venting problem, and all these things. So these are static equipment. Heat exchanger is not rotating equipment. So how do I predict the remaining life of my heat exchanger? It will be taking some of this abnormality and see how severe is the abnormality. And one of the way of predicting this remaining useful life of heat exchanger is to take the fouling index, okay, and also take the operating time, but applying machine learning model. Now, how it works is like this. You take the 1 or 2 years of heat exchanger data, but this is the difficult part. You need to identify the period where the heat exchanger is just finished the maintenance and is good, and then from that until it actually failed. Okay, then you take that parts of data and then you actually put it to the modeling studio. Okay, you put it to this guy, this little guy here. You put it to the modeling studio, then it will actually learn. Okay, using the either you can use a different approach. You will actually learn the trends and then the patterns of from good to bad. Once he actually learns it, okay, here is actually a regression, polynomial regression learning. Then it can actually use to predict the remaining useful life of the static equipment like heat exchanger. Compressor is not. I'm not talking about heat exchanger, but it's compressor is a rotating equipment. But if you look at compressor, the remaining useful life is calculated basically using polytrophic efficiency, or sometimes it's actually calculated using efficiency and operating time. So different equipment, you will have different. You will use different abnormal condition index, like fouling, like polytrophic efficiency drop, to actually predict the remaining useful life. Yeah, so different equipment is different. Yeah, but every equipment can have a remaining useful life predicted by machine learning. Yeah, using the right abnormal index. It's just like your body health, right? It's just like your cholesterol. Okay, my remaining life can be predicted using my cholesterol level. Right, that is my abnormal condition index. Yeah, but of course you need to take historical data of human population. What is the correlation between cholesterol level and the life, and from his good to bad to die to pass away?
Yeah.
Then you can predict. Yeah.
Yeah, by doing routine medical checkup, right? Okay. Another question from in the chat, Randy. How Kinet software work on real plant? In root cause failure analysis, input data need from input real plant such as sensor or modeling only?
Yeah.
So the question is the reality, real plant.
Yep. Now there is two software. I keep saying that there is two software. One is, if you remember my slide. So I know the time is limited, but I need to show this thing again. So there is two software. One is called the online. Okay. So I just make it bigger because okay. So this is actually the online. The online is taking data from DCS. Okay, so it's taking real-time data, and the modeling studio is taking data from historian, okay, from your historic, or taking the data from your OEM document. Okay, so different. So the online is taking real-time data, but because the model is created from historical data, when you put online, the model will receive real-time data, and then it will actually come up with the model calculated output. Because the model recognizes, oh, this is something that I encountered before when I look at the historical data, then this will be the output. You know what I mean? So the model will be, when you deploy, the model is created from historical data. But when you deploy online, when you deploy online here, all these are these real-time DCS or System 1 data, or any PRM, Yogawa PRM data. So these are, or any system data, real-time data. And then this is a real-time, take for example, this is a real-time efficiency. This is a model calculated predicted efficiency, okay, based on real-time input from DCS and from any other system like System 1 and so on, or MHM system.
Yeah, okay.
Okay.
Thank you.
Okay.
Last question.
Go ahead. Yeah.
Very last question. Some people said that machine learning or artificial intelligence will take their job. What do you think?
No, actually, no. It's not possible because the thing is, every of these prediction, you need human to actually to confirm, not analyze, confirm whether it's right. So, like when you actually see that there is take for example, he tells you that your make it bigger, so I screw up a bit. So any of this thing, it just helps you to solve the problem faster, but it doesn't actually replace your job. Yeah.
Yes,
so all these things, it find out this root cause for you, but you need to go and check whether your anti-surge valve is really too open. And for example, this boiler, right? I think this boiler, it tells you there is a boiler valve stuck at low position. Hey, you really need to check whether the boiler valve stuck at low position or not. The thing is, you don't need to actually go and a lot of problems, but I don't know what is the root cause. The system already figured out for you, but you just need to go and check whether it's real or not. Yeah. So you still need to confirm. Yeah. So it just make your time more efficient, and also spend more time on quality things that humans should focus on, not those things that is difficult for human to figure out.
Yeah. Good point. Thank you, Reggie. Okay. I think that's all. Thank you, Reggie.
So if there is any interest, please contact us. Contact Parojeki, and then Parojeki will bring you to us, and we can further discuss on specific use case of KNet in your equipment of interest.
Yes. Yeah. Thank you so much, Reggie.
Thank you.
Yeah.
Okay.
See you next time.
Thank you very much.
Yeah.
See you next time. Bye-bye.
Thank you.
Okay.
Stay healthy.
Yeah.
Keep safe.
Bye-bye.
Thank you.
Keep safe. Bye-bye.
Bye-bye. Oke, demikian Bapak Ibu webinar hari ini. Semoga bermanfaat. Keep healthy, stay safe, dan terima kasih.